Swayam Prabha. Digital India. Educated India.
So far we studied mesh analysis for circuits containing only resistors and independent voltage sources. Now we will consider other sources. Firstly the independent current source and then also the controlled sources. Okay. Let me take the circuit where here I have an independent current source. You recognize that this is the same circuit we had earlier, except that I replaced the resistor with an independent current source. Now, while writing mesh analysis equations, we had the voltage drops around each mesh to be equal to the voltage rise due to the independent voltage source in the mesh. Okay. The problem with the current source is that the voltage across the current source is unrelated to the current through the current source. You cannot infer the voltage across the current source from the current through the current source. The whole purpose of the current source is to maintain a constant current flow regardless of what voltage is across it. Okay. This is analogous to the problem we had with nodal analysis when we included independent voltage sources. Okay. And the solution is also similar to what we did with nodal analysis and independent voltage sources. Okay. So let me take the three meshes the same as before with mesh currents I1, I2 and I3. Okay. And the voltage across the current source, let me label that Vx. Now if I write the KVL equation around the first mesh, I will get I1 times R11 plus I1 minus I3 times R13, which are the voltage drops across R11 and R13. I don't know the voltage drop across this current source, so I'll just label that Vx, and that should be equal to the voltage rise V1. So this is for mesh number 1. Now for the second mesh, I know that I2 minus I3 times R23 plus I2 R22, and I don't know the voltage drop across this, and now I have to take it in the opposite direction. So I'll get minus Vx to be equal to minus V2. Okay. The problem is this Vx, which we don't know, and just like before we sum the equations corresponding to these two meshes and we'll get I1 R11 plus I1 minus I3 times R13 plus I2 minus I3 times R23 plus I2 R22 to be equal to V1 minus V2. Okay. Vx goes away because in mesh number 1 it appears with one sign, in mesh number 2 it appears with the opposite sign. Okay. And now what is this after all? This is basically the voltage drops if you go around this entire loop, which consists of these two meshes, and this is known as the super mesh, which is a combination of mesh number 1 and mesh number 2. Okay. So by forming a super mesh, we can eliminate this problem of not knowing the voltage across this independent current source. Okay. This is like forming a super node to not worry about the current that is flowing through the independent voltage source in nodal analysis. Of course, by combining two mesh equations into one, we have lost one equation, but we now also know by applying Kirchhoff's current law here that I1 minus I2 equals I0. Okay, because the current through this branch in the downwards direction is I1 minus I2, right? Here it should be I1 minus I2, but I know that value because the independent current source sets this current to be equal to I0. So I have the equation for the current source itself. And I get this equation, and with these two equations, and also for the third mesh, mesh number 3, I have the same equation as before. So with these three equations, I can solve for all three mesh currents, and from there get all the branch currents and branch voltages. Okay, so when you have an independent current source, you form a super mesh, right? And by doing that, you lose one mesh equation, but you have the constraint corresponding to the current source itself. That gives you another equation with which you can complete the set of equations required to solve for all the variables in the circuit. Okay, now we considered a current source which was between two meshes, but let's say there was a current source along the periphery of the circuit. Okay, something like this, and this is not in a branch that is common to two meshes, but that's in a branch that's on the periphery of the circuit, so it belongs to only one mesh. Now in this case, the situation is even simpler. You know that the current through this branch is the mesh current I1, and that has to be equal to I0 because of the independent current source. So this straight away gives you I1 equals I0, and you don't even have to solve for I1. Okay, now this is analogous to in nodal analysis. So this is mesh analysis, and in nodal analysis, let's say we had a voltage source, an independent voltage source between the reference node and one of the nodes. So let's say this is node 1. Number of other things could be connected to node 1, but the point is you don't have to solve for V1. You know V1 equals V0. Okay, so similarly, the situation of having a current source on the periphery of the circuit is analogous to this, where you don't even have to solve for this one variable. Okay, so the mesh analysis for planar circuits is analogous to nodal analysis in a lot of ways. The easiest case for nodal analysis is to have only resistors and independent current sources. The easiest case for mesh analysis is to have only resistors and independent voltage sources. Now in nodal analysis, when you have an independent voltage source, you have to form a super node by combining two nodes. In case of mesh analysis, you have to form a super mesh by combining two meshes. Now I said two, but that depends on how the voltage sources are connected. You know that in some cases, if you have a chain of voltage sources in nodal analysis, you may have to combine more than two nodes into a super node. Similarly, in mesh analysis also, if you have current sources in many branches of the circuit, you may have to form a super mesh, which is a combination of more than two meshes. Okay, so all of this is possible, and these situations are analogous. That's why I'm not considering them in great detail, and I'm going relatively quickly through them. Okay, so if you compare the two, mesh analysis easiest when you have circuit with resistors and independent voltage sources, and for nodal analysis it is for circuits with resistors and independent current sources. Okay, and in these cases the structure also is similar. We have the resistance matrix times the mesh current vector to be equal to the source vector consisting of independent voltage sources, and in case of nodal analysis we had the conductance matrix times the node voltage vector equaling the independent current source vector. And also these had similar structures. They were symmetric, and if you look at the diagonals, in this case it was sum of conductances at a node, and in the case of mesh analysis it was sum of resistances in a mesh, and off diagonal elements were also similar. In case of nodal analysis, the off diagonal element was the negative of the conductance between two particular nodes, and similarly in mesh analysis it was the negative of the resistance common to two meshes. Okay, and when you include current sources with mesh analysis, we have to form a super mesh, and this is similar to having independent voltage sources with nodal analysis, in which case you have to form a super node. Okay, so with this analogy and the detailed treatment of nodal analysis you have gone through, you should also be able to do mesh analysis and understand its properties for all cases. Okay.